Good morning. So this is the last slide we discussed yesterday. And before we move on, any questions? On the internet, people, everybody understood everything. Apparently, yes. So let's go on. Now we start with variabilities, random and systematic effects. Most of what I'm going to explain, you actually have already heard, even in this lecture, let's say to some extent, but not very deeply. Now we go deeper into the same thing, so we have to make some things very, very clear, in order to be able later on to use these concepts in reasonable way. So first of all, what random and systematic mean is here. I think I don't really need to explain much here. It is, I think, very obvious what is going on. Yeah. So if your results tend to be on an average on one side of the true value, then obviously you have a systematic effect. And if your results do not agree among themselves, you have a big random effect also. In this case, the systematic effect is negligible because although they all differ from the true value, but their average actually matches pretty well. Random effect is big. In this case, the random effect is small. Yeah, they agree with each other pretty well, but there's big systematic effect. Yeah, they all on biased to the one side. And finally, here we don't have any random or any systematic effect. I guess this is something you all know. But in few slides, we will find out that the like assignment of whether something is random or systematic is not absolute, but depends on time frame. This is also, we briefly already mentioned that, but now we will be looking at it. But first of all, let us look at terms that characterize variability of results, so that if your results either do not agree among themselves, or they are biased, meaning they are like all on one side of the true value. How do we call these things, and then what can we do? First type or first kind of precision is repeatability. So repeatability is the type of precision that characterizes this measurement situation. So you made measurements with identical samples. Identical means as closely identical as possible. Yeah, in real life, it might not be possible to have absolutely identical, but still as similar as possible samples. Under the same conditions. If you do that, then the standard deviation or the variability of the results characterizes the repeatability. So repeatability characterizes agreement between replicate measurements carried out exactly under the same conditions. And also, almost always, this is interpreted in such a way that all these measurements have to be done within the same day or within the same run. By run, I mean, you remember those dots, yeah, on the slides. By run, I mean that, okay, you put a lot of samples into autosampler and now you start the system. That does not mean that it has to be the same calendar day. Yeah, you start it today, but maybe it stretches overnight and only ends tomorrow morning. This is still considered the same day or still considered repeatable. Repeatability obviously describes random effects, and repeatability is interesting in the sense that the random effects that the repeatability describes really are random under any conditions. And I'll come to that, why some random effects are not random under. And also, in almost all cases, especially if we use this term S with small r, this is like the way how people typically denote repeatability. In almost all cases, interesting for us is method repeatability, not instrument repeatability. Yeah, okay. I said almost all cases. That's not maybe well said. Sometimes if we do the isogamy evaluation, then actually we're also interested in repeatabilities of specific steps. Yeah, like just repeatability of weighing or pipetting or whatever that. Okay. Perhaps I stop for a moment. Good morning. Stop for a moment and ask if you have questions. Okay. And now, if you speak about method repeatability, this automatically means this, that all steps of the method have to be included. Why I'm stressing that? People often want to determine repeatability in such a way that, okay, I have here a soil sample. Yeah, it's very complex sample preparation. I do all the manipulations. Now I get the solution. Yeah, okay, here it is. And now I inject this solution 5 times into my instruments. I get 5 results. I calculate standard deviation, and I consider this my repeatability. What is wrong with this approach? Yeah, sampling, absolutely not. But let's assume we only want to present the result for the sample. So sampling is not relevant. What is then wrong? Exactly. The repeatability that we will then get is not your method repeatability. It is the repeatability of the instrumental part only, disregarding sample preparation. And as you may remember from our previous lectures, sample preparation oftentimes is one of the biggest, if not the biggest source of uncertainty. And also sample preparation repeatability tends to be like quite big, yeah, quite variable. So that person who does it like that most likely grossly underestimates the repeat. Instead, what he or she should do, okay, here's my sample. I take 6 of, I think it was 5 subsamples. I make separate sample preparation for each of those 5. I now get 5 solutions. And now we inject each of those into the instrument. This is the correct way of doing method repeatability, or evaluating method repeatability. Since this is very important, could you please raise your hand who thinks that understood this logic? Okay, thank you. People on the internet. Hi there. Good. All right. Now the next thing, which also might be obvious, I guess, is that repeatability is rarely, if ever, the only source of uncertainty. So what people sometimes do, if they are not really educated at all in all this measurement uncertainty thing, is, okay, yeah, good, I have here my sample, I analyze it 3 times, get 3 results, I calculate standard deviation, oh, very good, this is the measurement uncertainty. This is almost never true. and it is almost never true. Why? Yeah, but that if repeatability is correctly evaluated, then all the steps are included. Exactly. Those steps might also have systematic effects influencing them, meaning you can have very good repeatability, yeah, exactly as you see here, yeah. Person is very happy, yeah, but actually his result is completely off, yeah, because there's some systematic effect that influences the same way all these 3 or 5 or however many replicates the person. All right. Now, here is another question for you. How is method repeatability related to weighing, pipetting, and instrument repeatability? It's actually pretty important and pretty useful thing to think about. So, if you determine method repeatability, including all the steps, starting from sample preparation up to the final result, how is this repeatability related to repeatability? So, for example, these individual steps. Dave, could you take microphone also?
My best guess is that the method repeatability encompasses everything that is included in the method that may cause some repeatability issues. Weighing, pipetting, and instrument regard only this specific part of the whole method.
Beautiful. Brilliant. Exactly. So if you determine method repeatability, starting from the very beginning to the very end, then this SRW, yeah, will encompass or will embrace all the repeatabilities of all those steps. So that in principle, if you run the method like that, you don't, or if you use this overall method repeatability for evaluating measurement uncertainty, for example, you don't really need to separately account for weighing repeatability and pipetting repeatability and so on and so on. Okay, good. Now, the next possible precision, or actually set of precisions, is called reproducibility. Here, there's again some terminological, maybe some incoherence with how I explain here and how some other people see it, but the incoherence is not very big. So we can say that reproducibility is precision if you do, again, identical samples for the same sample as close as possible, but under changed conditions. Something changes. Repeatability determination, or if we speak about repeatability, everything is exactly under the same conditions as far as possible. But here it is the changed condition. And again, if we determine method reproducibility, then of course, again, all steps have to be included, including sample preparation. And if the method is not, if your result that you present is not for the sample, but for the whole object, then you also need to include sampling. Now, the change can be different things. There can be different kinds of changes. And the first type of change that we could in principle consider is that the same sample is analyzed in a completely different lab. And this is then called between lab reproducibility. And sometimes people also call this kind of reproducibility simply reproducibility. So if you see simply somebody says reproducibility and nothing is explained what it is, then it often is between lab reproducibility. Okay. But now, the most useful and most interesting and most important type of reproducibility for us in this course is something that can be called within lab reproducibility. This is how I also, I think, mostly call it in the online course, but more recently now people prefer the term intermediate precision. And there are different ways of denoting it, but in this course we denote it like this, SRW. R and W mean reproducibility within lab. Yeah, so this is where the R and RW. What this intermediate precision or within lab reproducibility means, it means it's the same lab, the same or identical sample, the same method, but maybe let me now take completely different color. But it is different days, different kinds of solutions. What by that I mean, let's say standard solution, derivatization reagent solution, some buffer solution, different eluent for liquid chromatography, etc. It can be different analysts. Yeah, suppose in some lab there are two people who do this kind of analysis. Sometimes one person does, the other day the other person does. You know? It can be different ambient conditions. Like today, the temperature outside is 0, yeah. Some other day it's +20, some other day it's -20, which, for example, influences very much the air humidity in the room. Yeah, if it's -20, then air humidity here is very low. Yeah, if it's +20 in some air humidity, right? And also inside room temperature. And you see there is ETC here, etc., which tells us that in principle, and now this is very important, any normal routine change occurring in the lab, in the normal operation of the lab. What do I mean by that? Okay, let's say purification cartridges of water purification machine were replaced. Yeah, this is a change. Then one column of your GCMS is now quite old. Yeah, you replace the column. Then somebody or like technician came and cleaned the injector and cleaned maybe the detector, or maybe the detector was completely replaced. Yeah, etc., etc. So all normal, usual, routine maintenance procedures also count as those changes. Now, let's try to analyze one thing. Suppose this is an example which we already have. I already have told you this, but I now come back to this because it is like perhaps the best understandable. Let us assume that you do some kind of analysis with calibration graph, as it is almost always done in instrumental analysis. And every day you do a new calibration graph. Every day that you do the analysis, of course, the calibration graph, you do it as well as you can, yeah, possibly with replicate sums, etc. But I think we all agree, every day your calibration graph is slightly off from the ideal, absolutely true calibration. Some is like higher, some is like lower, yeah. So, do you agree with me that within a specific day, if you use the same calibration graph for all the samples, the calibration graph influence is a systematic influence? Okay, so within the same day, you can make however many replicates, but the agreement between replicates does not give you any information how much off was your calibration graph because it is the same calibration graph throughout the day. So repeatability does not take that into account. But what about within lab reproducibility? So is this effect of calibration graph being off, let's say being not very correct, yeah, some random effect in calibration graph, is this random effect accounted for by SRW, by the intermediate precision? If on every day we do a different calibration graph. Okay, yes, it is. Sometimes the graph is higher, sometimes lower, so sometimes your results are higher, sometimes lower, yeah. So that in the long term, over a number of days, yeah, and this is exactly what is meant here, different days, yeah, see, this is different days, yeah. Over a number of days, the calibration graph being slightly off becomes a random effect, while within a day it is a systematic. Please raise your hand who thinks that understood this logic. On the internet? Either? Okay. This is now extremely important, and this is now a very good demonstration. The effect of calibration graph on your analysis can be either random or systematic, depending on the time frame that you are looking at. So that the notion random effect, systematic effect, most of the time is not absolute, but relative depending on time frame. But sometimes a random effect really is always random. Sometimes a systematic effect really is always systematic. A random effect which is always random is that if you analyze each of your samples in 3 replicates, then this is random within a day and it still remains random in the long term also. And systematic effect, which is always systematic both within day and over the long run, are those systematic effects that are inherent in your method or inherent in your equipment or something that you use. They are sometimes called method bias or lab bias. Some example could be, for example, if you do such a thing as determining moisture content by drying in a drying oven, then there are certain ways how this can be done, but if you heat it insufficiently and you do it always the same way, you get slightly lower results than you should, and it always be somewhat lower. So that is systematic within a day and remains systematic in the long. Let me stop. Maybe still you have some questions. I will do I will do more explanations in the coming slides, but let's see if already now you want to ask something. Okay, if not, let's continue. So, in this course, when I say reproducibility without giving any details, then I mean within lab reproducibility. Because again, within lab reproducibility is more useful than any of these other reproducibilities for our purpose. But then it does not stop there. You can have different other kinds of reproducibilities. For example, you can look at between person reproducibility. Yeah, you ask the same sample to analyze both of the two analysts. Yeah, there are two or maybe three analysts on your, and you see how well their results agree. It can be between instrument reproducibility. For example, you have two GCMS systems. You run exact same samples in those GCMS systems to see how much biased is one or the other, yeah, etc. But those are usually so useful. You can get some information, but there's not so much that you can do with that. Such reproducibilities might be necessary and interesting in some very specific cases. For example, if you specifically are investigating the instrument, but your aim is not so much the samples, but to like qualify which of these instruments really is better, for example. So this is when it comes into play. So routine laboratories don't really use it very much. For a routine laboratory, it is very clear that this reproducibility within lab reproducibility is certainly the most useful. And if reproducibility is quoted, then actually it's a very good idea always to specify what is changed. Whether it's between lab reproducibility or between analyst reproducibility. But if you read intermediate precision, then this always means within lab reproducibility. So intermediate precision is in that sense a very good term, that there's no ambiguity at all. And this intermediate precision right now is actually the preferred term. All right. Now, what I already explained is also to some extent explained here now. So this within lab reproducibility or intermediate precision, in addition to taking into account purely random effects, it also accounts for some systematic effects, as I just explained. And here is another example. I had an example about calibration graph, but here is a titration example. So if you redetermine titrant concentration every day when you use that titration method, then every day you determine it slightly off. It always has some uncertainty. And that uncertainty within the day is a systematic effect, because all your samples that you analyze on that day are influenced by that titrant concentration. However many replicates you make, you cannot catch that titrant effect into repeatability. You can have beautiful repeatability, but because of titrant, you can still be quite a bit off. But between days, it is largely a random effect. Exactly the same way as with the calibration. Can anybody say why the word largely is put here? Why did I put this word here? It is always a random effect, but not only random. It can also contain some systematic component. So that, for example, when you determine the titrant concentration, you might also do some, or you might also be influenced by some systematic. So that largely it becomes random, but some residual systematic effect might also remain within. Now, a big generalization is here. The longer is the time frame, the more effects change their status so that they become from systematic into random. And this now can be explained with this slide. So if we think that like this width here characterizes all effects that cause uncertainty, or all uncertainty sources, then if you look at it only in the short term, let's say within a day perspective, then a very large share of your uncertainty sources are in this bias section or systematic effect section. Some are here in repeatability. So you see, repeatability does account for some uncertainty, no? But oftentimes those within the systematic effects or within the bias, those effects oftentimes are much bigger than the repeatability. So that if you calculate repeatability standard deviation, it can be more than 2 times smaller than your actual measurement uncertainty. Not always so, but can be. But now, when you do it, when you do your measurement in the long term, then you see that this share of the systematic effects will actually move here. So a lot of systematic effects will become random, like the calibration graph effect that I just now, right now. Also, let me try to give another example. When you work in chromatography, your column becomes older and older, yeah? Which means that typically resolution becomes worse and worse. Okay, peaks are still more or less resolved, and not so well anymore, so that gradually you might be introducing some bias, because when you integrate, you already will like slightly integrate also some other peak into your peak. So you sort of start getting somewhat biased results. Within a day, that bias can be like, I mean, within a day, all your results are biased, because all the time some interferent which with a brand new column does not really influence, but now already influence somewhat, will slightly interfere with your result. But then when you change the column, this goes away. So that sometimes it's there, sometimes it's not. So over the long term, again, from systematic, it becomes largely random. Some systematic part may remain, but largely it becomes. And this long-term bias is bias which still remains, or systematic effects which still remain even if you analyze the same sample over many months, or even several years. And this is, as I already said, oftentimes called lab or method bias. So this is something that is always systematically shifting your results away from the true value. A very typical lab or method bias also is that it is simply some trace analysis with difficult matrices, again, soil, meat, yeah, you name it, where almost always you have some analyte losses. Most of the time you have, like, let's say, recovery 90% or something. And that is always so, whichever, like column or detector replacement or cleaning or new derivatization reagent or new calibration graph, etc. You always lose some analyte during sample preparation. And this then is your method and or laboratory bias, which does not become random over a long period. True, if your sample preparation recovery is 90%, then what that means is that it's on an average 90%. Individual cases might be 94, 87, 92, 88, 91, 93, yeah, so that on an average it is 90. So there is a systematic effect, but overlaid upon it is a random effect, which is just, let's say, the repeatability or reproducibility of sample preparation. And that random effect of sample preparation, of course, will be sitting here, obviously. And also, it's oftentimes asked, yeah, okay, long term, how long is long? Let's say, ideally, it's 1 year. But it's also, let's say, many months. 6 months is also pretty okay. 1 month typically is not long, for a few weeks. It's still months, and it is typically good if within that long time period, there are all kinds of maintenance things, changes of solvent batches, changes of derivatization reagent batches, I don't know, new solid phase extraction cartridges were bought, yeah, the other ones were exhausted, so that a lot of those typical changes would happen during that. During a very short period of time, something that might cause bias just does not change, so that bias will remain. But over the long term, the bias might go away or go the other way, in different direction. Now I see. Oh, Luis, very sorry. I have neglected your question 1028. Let's see, because in the steps error could be. Yeah, okay. This 1028 comment, I'm not unable to comment. Very sorry for that. I did not notice in the right time. I cannot say now, and I don't know what I could reply. But now I'm looking at your 1051 comment. The long-term bias can be identified and correct or lowered in the long term, or is it the condition that's always present? That's a good one. Yeah, I'll come to that. So indeed, you can easily determine this SRW simply by having some control sample and analyzing it. Like on every day you analyze this, you use your method over a long time period, and you simply calculate the standard deviation, and this is what it is. So it's very easy to determine. Determining long-term bias is not easy. I have a slide here quite soon where I explain a little bit, but later on in this course, I explain also more deeply. So I also will give you some ideas how to evaluate bias. And this is actually, so Luis, long-term bias can be identified and corrected, but with drawbacks, let's put it. Yeah, so it's it's certainly not easy. But now I actually almost already answered this question, but let me now still ask you. So which is easier to reveal and quantify? Random or systematic? Why random? Take microphone. My turn.
Of my attention that you say that the intermediate precision, it was relatively easy because you just have to control sample and then measure during different days, but long term could be not so straightforward.
Yeah, you mean long-term bias is not straightforward.
Yeah.
Yes. Yeah, exactly. Yeah, I essentially answered that question myself. Yes. So determining precision is almost always fundamentally much easier than determining bias, because precision always, in principle, can be determined by making a replicate. And for SRW, all you need essentially is sufficient quantity of sufficiently stable control sample. What people sometimes do, for example, you could say, oh yeah, but my sample is not so stable. Yeah, I'm analyzing raw meat, for example. But raw meat can very well be preserved in freezers, the same type of freezer as you have in your home. Yeah, raw meat can stay there for months and months without essentially any problem at all. So you can take the meat, yeah, mince it, yeah, make it like minced meat. So it is not one piece, but like a mass, yeah. That minced meat can then be packaged into small like packages or small samples. Those can all be put into the deep freezer. And every day you do your meat analysis, you also take one sample from there and include inside your analysis. And if you homogenize that meat well, sufficiently homogeneous, if you put sufficient amount, you can run for months, maybe even for years, that meat sample all the time, you analyze it. And you can very nicely calculate the SRW just as standard deviation of the results that you obtain on all those different.
So in that example, you need to like repeat the same procedure, the same analytical procedure every time that you need to carry out your analysis. Not just, for example, I prepare a solution, I store it on the fridge, and I just measure it during those times. You need to repeat also the
yes. If you want the intermediate precision to be your method's intermediate precision, not just the instrumental step, then I need to start always with sample preparation. This can sometimes be tricky. Okay, this meat is actually not so difficult, but there are situations when you cannot keep such long-term control sample because you cannot get sufficient amount. For example, I can give you a very. This is an example that Professor Bergqvist, by the way, is very much involved in. So those of you who go to Uppsala might be also involved in some things. Professor Bergqvist, I don't know if you know that he's by education actually a doctor, not a chemist. He's fundamentally a doctor who has learned a lot of chemistry and now is professor of analytical. But being doctor gives him extremely good understanding of all the human body and everything, which is very, very, very useful for chemical analysis if you know your object. And Professor Bergqvist is also involved with newborn babies. For example, something very useful analysis is cerebrospinal fluid of newborn babies. Now you can imagine you cannot get liters of that. You cannot get milliliters of it. It's only microliters that you operate. Even that is very difficult. So I cannot imagine how Professor Bergqvist could have a half a liter control sample somewhere in the fridge. He simply cannot. So there's oftentimes such kinds of analysis where you simply cannot get enough of the sample. Most of the time, that's not an issue. So, for example, if you do some food control, fruits, vegetables, etc., you can get kilos of bananas or oranges without any problem at all. Yeah? Or meat, that's all very easy. Soil usually is not a problem in terms of quantity. But those medical bio things sometimes are. This control sample thing we will revisit in more detail in the quality control part of this course, where we speak about something that is called control chart. I will have to explain control charts to you actually already before a little bit, but they will come. Yeah? And control charts are essentially based on running some control sample every now and then and making conclusions on the basis of that control. All right. Any questions here?
Example, in the example that you have just mentioned, in that case, we could not be able to get the intermediate precision of the procedure, right, in the long time, because there is not enough control sample. It's impossible.
We cannot do it this way. It still is possible, but in a more complex way. Yeah? We will get to that. And I will explain how this SRW actually can be run also in such a case if you don't have a large amount of control. Yeah. Could you take microphone? Yeah.
It isn't a question, but sort of a realization or dilemma. So, at first, my question is there a golden rule when you consider intermediate precision, how long? But you've already answered that. But in terms of the intermediate precision per se, is it really that critical or crucial to include it in a routine sample in terms of a testing lab? Because as a testing lab, I wouldn't perform the samples, customer samples, in multiple days just to include the intermediate precision. It would much be logical to do that in method validation, but it would be, there's a trade-off of how long should I perform the method validation to be able to use that right away for the customer sample. That is it really that crucial for this component to be included or even be considered? Yeah.
Very nice question. Again, I can only praise you for the good questions. What you are implying is that, look, should determine intermediate precision already during validation. Yeah, we should already know before we start offering services to the customer. This is true. Yes, we should. But when we come to the validation part, I will try to demonstrate to you that method development, method validation, and actually method use quite a bit overlap. And for example, if I say, yeah, you should do certainly 1 year for intermediate precision, this would automatically mean that, okay, if today there's a customer wishing some kind of analysis, and I say, yeah, okay, I don't have a method for that, but I can develop it for you. But look, I need 1 year for doing the intermediate precision or determining intermediate precision. Yeah, then please come back next Christmas. Yeah, then I will give you the sum, and probably the customer will walk away and probably will not come back. So that what I usually say is that during validation, yes, you do as much as you can, but you never stop. I have, not in this, but in the future, in quite some slides, I have just the phrase, never stop. What that means is the following. You start your method development. Already during development, if from some point on you don't change, for example, sample preparation, etc., maybe you are only like determining some parameters, already then you can collect quite a number of data for the SRW. But during routine work, you continue collect. So that if after the validation, before starting offering services to customers, you have already some estimate of SRW, but over time, you can improve it, can get better and better, like more and more reliable estimate. This is like point number one. Point number two is that even if you determine your method and validate it, your SRW may change over time. Not really sure that it will always be the same. On one hand, when you develop your method, you are still not very skillful. Yeah, you are only starting. Maybe in 1 year, you are much more skillful. Your SRW is smaller. On the other hand, maybe you leave that laboratory, somebody else comes and takes over. He, in the beginning, is not so skillful, or SRW goes up. So it is very useful. I just cannot stress enough how useful it is to monitor it. I'm going to stress that also in the future. And now comes my answer number three. I think probably all of you agree that control chart samples we should always include into our runs. But those control chart samples are those that can be used for SRW determination. So that the information flows automatically to you without you needing to do extra effort. Why not use that data? So that what I would typically recommend is that, yes, 8 months is pretty good, 1 year is better. But suppose now the method has been in use for several years. Then I would say just discard gradually older data and always include maybe the last 1 year or the last 2 years or the last, I don't know, 20 months or the last 15 months, etc. So that you always have your SRW estimate which corresponds your most recent like performance, how good you are. Did I manage to reply? Yeah. So it is the problem that oftentimes puzzles me and what actually disturbs me, and where I sometimes am at odds with some other recommendation from some other people, is that, in my opinion, it is not possible to strictly separate method development, method validation, method use. These things overlap. For example, when we come to validation, and I'm going to tell you about limit of detection and limit of quantification, these are really tricky things. They are much more tricky things than SRW. My recommendation is, every now and then, redetermine your LOD, because LOD, limit of detection, is extremely changing. Extremely changing. It depends on small nuances that can shift your LOD like this. Yeah. And if you just determined it at some point during validation, which maybe was 3 years ago, it's not necessarily the same today here. So that, yeah, there are some things that you probably don't need to redetermine, either not at all or at least not often. But SRW, I certainly would recommend to keep your eye on, especially because with control chart samples, you can do it with minimal effort, because control chart you should run anyhow. This is something that I would absolutely strongly stress. Every time you run some kind of method, put your control sample so that you can see whether those values more or less match. And if on one day suddenly, oh, why so low? Then you know that something is wrong. And before sending results to customers, you should stop, you should take everything apart and start investigating what is going on. And this, of course, is not my invention. Yeah, this comes from the ISO 17025 requirements and so on and so forth. Necessary. Okay, yeah, I hope I managed to reply. But now there's a question from Louis. The intermediate precision includes the random effects in sample preparation. Yes, it does, like pipetting or weighing. Yes, it does. Or is it just the standard deviation with controls, instrumental value? No. Intermediate precision includes all random effects. Yes, all within the random effects are automatically included. And those random effects that over the long those effects that over the long term become random are also included. But all within the random effects are certainly included in intermediate precision. Luis, did I manage to answer you? All right. So, any other questions? Mike Tanner, yeah. Would you pass the cubic? Yeah. Yeah.
I have a question there, because in the last slide you say, I was thinking about the word largely, because you mentioned that it can also contain remaining systematic effects. But
yeah.
like in the next slide, I understand, or please correct me, like the repeatability just in one day, or the intermediate precision just takes into account like the variability. It could be within the day or like during a longer period of time. And the bias is the remaining systematic effects. And like when you put them together, you're gonna, I imagine, have the combined uncertainty. But how can it be possible that the intermediate precision has also systematic effects remaining there? Like the ones that are always systematic, they are considered in SRW or in long-term bias calculations?
Let me try to explain this on the example of this titrant. Yeah. So suppose you have some like standard substance with which you determine the titrant concentration. You have a big pot of it, so you don't buy it every year. It's there for years. Yeah, it's always the same. Yeah, so always you have the same standard substance. But that standard substance has some purity, which is not 100.00000%. Yeah, it's probably somewhat lower. So what now happens is the following. If you determine your titrant concentration today, your determination will have, let's say, random effect. Let's put it just repeatability. Yeah, you made like 3 or 5 titrations. Okay, you calculated the average. And this is now what you use for your work. So these random effects in all your today's samples will be systematic. Because you only use the average. This average, of course, is off from the true titrant concentration. Yeah? And today it will be a systematic effect, but over long time, these random effects will become random. Because sometimes your average is slightly lower, sometimes it's slightly higher. Yeah? So that the random effects of determining titrant concentration within they will work as systematic effects, in the long term will work as random effects. But now superimposed on all that is this purity question. Suppose it's not 100.0000%, but suppose it's 99.7%. It's very little difference, but still. And suppose you don't take that into account, you don't care at all. Yeah, you think it's 100. Yeah, you don't take the purity into account in any way. Then, in all cases, today, next day, next month, and next year, your titrant, your real titrant concentration is actually always slightly smaller than you think. And that is a bias, which is a bias within the day and is also bias in the long term. Because as I said, suppose your standard substance is there all the time, yeah, you don't change it. Just take from the same pot all the time. Did I manage to explain?
Yeah, and this will be the systematic effect that it's remaining. But like its contribution will be taken into account by the intermediate precision or the long-term bias calculations.
The purity.
Because I understood that the SRW and repeatability just take into account the variability of our data, but that is always a systematic effect.
Yes, and that will be, that purity thing will be sitting in long-term bias.
Mm-hmm.
But the repeatability of titrant standardization will be sitting here in the intermediate precision. But within the day, it will be sitting in the within-day bias. Did I manage to explain?
Yeah.
So you see, the word systematic and random, not so easy. You find those easy sentences in every manual, but once you start looking slightly closer into this, it's not so obvious always what is systematic and what is bias under certain conditions. I think if you think about it, you probably can manage to think about all effects, how they are. Okay, yeah, this is within day, it causes systematic effect, but yes, over the long term, it will even out, so it will be a random effect. But this thing, which always is the same, yeah, will still remain biased over the long term. It is quite important to be able to like sense which way it is, and what will be converted into random effects long term and what will. Okay, now here is some rule of thumb. How should repeatability, intermediate precision, and combined standard uncertainty be related to each other? Repeatability takes into account only within-day random effects. Any within-day systematic effect is neglected, so it should be the smallest of all these. SRW takes into account within the random effects and also long-term random effects, which within they might be systematic. So SRW is bigger than repeatability by the amount of this rectangle here. Yeah. So these are all things that within lab reproducibility takes into account, but repeatability does not take it. This is why SRW is bigger than SR. Yeah? You see here also the bars are different. Yeah? But then combined standard uncertainty, if we speak about the combined standard uncertainty of your overall method, has to account for also those systematic effects which remain systematic long term. Yeah? So that combined standard uncertainty is as big as this bar here now. Yeah? So it has to encompass everything. No. So this bar now is like characterizes the magnitude of the combined standard uncertainty. That one has to be. Now, there are two interesting questions here. First of all, let us take this one. Can this be possible? Or when can this be? Let me say, yes, it can be possible. But what is the condition for this? What is the condition for this thing? Brilliant. Sadly, today is not exam. Yeah? Otherwise, you could get nice points. Yeah, exactly. So our method does not have long-term bias at all. So this rectangle has disappeared, and this red rectangle stretches up to here. And this is fully possible. If there is no such, let's say, inherent deficiencies, inherent method bias, and let's say maybe it's not some trace analysis of soil, but some, let's say, more or less average concentrations in analysis of macro components, then this can very easily happen. Yeah. And also, even trace analysis in soil, you can correct for bias, and we will look into that later on. Yeah. Or we often call it recovery correction. Yeah. This is a very tricky topic, but in principle can be corrected. So yes, you can have such a situation that you don't have long-term bias. Okay. So that this is possible. I would say most of the time it is not. Most of the time it is still like here in the yellow rectangle. But now my question is here. If you do experiment now determining repeatability, yeah, you determine repeatability and you determine within lab reproducibility, get both standard deviations, and suddenly you see that instead of repeatability being smaller than a certain, it's the other way around. What does that mean, or what could be the reason for this? Yep.
I actually wanted to ask about this a bit previously, but since I guess now is the right time, I guess it's obvious from the previous chart that for this to happen, some of your random effects have to become systematic in some way. And I have no way of envisioning how this might happen.
This cannot happen. Yeah, we can very confidently assume this cannot happen. If something is random already within the day, it cannot suddenly become systematic over the long term, because the long term is also composed of days. Yeah, you're doing all the same manipulations also in the long term. But let me draw your attention to one phrase here. If your experiment I did not catch what you said.
Maybe we are doing something wrong, or we are doing sloppy practices.
Yeah, this is also possible that you are doing something literally wrong. But let's assume it's not. You're not sloppy. You're not doing anything like really wrong. But there's something which is insufficient. Let's put it this way. Yeah, Maita?
The person are becoming more and more skillful.
No, I did not mean that. No, That is also possible, yes, if person was not skillful and then determined SR and finally was very skillful, determined SRW, then indeed it might happen. But we assume that the level of skill is the same. Yeah, it's the same state of the method. Would you explain?
Maybe that repeatability that accounts for the same day, maybe it just so happens that you got the nicest results for your instrumentation, for your method, and it just doesn't hold well enough in the long term.
Mm-hmm. Could you try to rephrase it into some mathematical, statistical term? Yeah? In principle, you are very close.
So we, on one particular day, we just happened to measure our measurand as close to the true value as possible. Just so happens that we did it without doing anything particularly right or wrong.
It can happen, yeah. Since any individual measurement is a random quantity, they indeed can just happen to be very close. And what to do against that?
Why would you want to do something about it? It's a nice thing to have.
I'll come. It's extremely good that you said. I will come to this. Why this is not nice thing to have, but still, let's assume it's exactly as Gleb said. So on that day when you determined SR, you simply happen to have very nicely agreed. Since they are all random, this indeed can happen. What could we do to get a more realistic SR, more realistic repeatability? There's a very simple answer to that. More replicates, exactly. So this kind of thing in laboratory almost always means not enough replicates. Very simple. I haven't, I'll come to what I promised, but I haven't done that math myself, and I'm not really sure how to do it, actually. I should learn some of it. But I have heard such a statement that if you do 5 replicate measurements and you calculate the standard deviation, then the standard deviation of that standard deviation is something like 30%. And now you can close your eyes and think what would be the standard deviation of the standard if you do only 3 replicates, which is a very common thing to do. It's huge. So if you do 3 replicates of repeatability and 3 replicates of SRW, it is not at all strange or unexpected if you get this kind of thing. I would say to get these values right, I would say at least 10 replicates. But to do 10 replicates within a day is not so easy. But I will teach you later on. Sadly, I think we will not reach there today. I will teach you later on how to do that. So that almost always it's insufficient number of replicates. Now, Gleb, I have to explain why this is not so good. Yeah? If you determine repeatability and you are so lucky that the result just happened to be very close, you put that extremely optimistic repeatability into your uncertainty calculus, show to your customers, oh, see how good I am. But in the future, you will not have that same level of luck. And you will be presenting underestimated uncertainty. So this is why it is very important when you determine for your method this repeatability and within lab reproducibility, it should be as realistic as possible, not pushed down artificially. Did I manage to explain?
Kind of asked general conclusion.
True.
Never.
Artificially, no, but really, absolutely, yes. So, of course, you should try to improve your method, become better, but yeah, but artificially, no. I certainly can get on a very slippery road. Yeah, you can end up in court and all kinds of nasty things. All right, so let's see. This I wanted simply, I've put this in simply to explain where we can get this intermediate precision data, but I think this I already explained. Yeah? The control chart samples are the means. Now, I've been saying several times now, I think, that systematic effects are more difficult to evaluate. We will not do systematic effect evaluation today here because it would it's a lot of work. It's not so easy, but I will still give you some general idea how that in principle could be done. In like very broad terms, there are 4 approaches how you can evaluate this long-term bias. Option number 1, you buy a certified reference material and compare your result with that. And of course, if you want to evaluate systematic effect, then what is meant here by your result? What do you think? What should we specify here additionally? Just one result or? Average of a number of replicates, because every one result is of course influenced both by systematic and by random effects. Yeah? So average result. Wow. Right? Yeah. This is a very good approach, but sadly not for all analyte matrix concentration combinations you can find certified reference. You do something very mainstream like lead in drinking water, then you find certain, yeah. But if it's slightly less common analyte and slightly less common matrix, most probably such reference materials are not on sale. Okay. The next thing is that you find some lab which is extremely skillful and has some very high level people, very high level methods, etc., very well established, and ask them to analyze your sample, so that they would analyze your sample with much lower uncertainty. Yeah? And then again, you can compare the average of your result with them and see how much you are. Here, the main problem is that usually you just don't find it. Very often you are the lab of, like in your country, who is, let's say, one of the best or maybe even the best. There's not much where to go. On the other hand, if you find such lab, they will really charge you a lot. It will probably take a lot of time. They might not be interested. So it is not the general way of doing. Sometimes it is possible. And if it is possible, it's a very nice way. Because you can, if you look here, it is reference material, which is not exactly your sample. It's something else. But the second option will enable you to get the reference value for your sample, the same sample that you have. This is more valuable than CRM, certified reference material, because that is still a different thing. But yeah, sadly, you usually don't find such high level reference. The next thing, which might in principle be the most easily doable, is spiking. So you take your sample in principle. It can even contain the analyte, no problem. Now you weigh carefully how much sample you add, and you add a very well measured amount of the analyte. Now you mix well, so that the analyte is dispersed in the sample, and now you run with this same sample again your analysis. And of course, you have to run with that same sample before adding. And you know how much higher your result should now be, how much you added, and you see how this difference of now your two method results compares to how much you added. This is a very typical way of determining recovery. The good news here is that you can again work with your own sample, so that matrix matching is absolutely like perfect. Yeah, good. Also, you are not dependent on whether anybody is selling it or not, and so on. So you can use. But the main trouble is how you disperse the analyte the same way as it already is in that sample in native way. Again, if I think about soil, if you think about, let's put it lead in soil, for example. Yeah. That lead might be in the mineral part, it might be in the sand, it might be in the organic part. Now, if you add lead, how do you guarantee that your added lead will go into all those same fractions the same way? It's almost impossible. Especially if part of the lead in soil is sitting inside that mineral part. Your added lead certainly will not penetrate into some small sand piece of sand, but original lead is there. So your lead, which you added, will not behave the same way. And therefore, what is very often the trouble with spiking is that you get quite optimistic recoveries. Oh, no bias, recovery 100%, good. But in reality, not so good, yeah, because you did not manage to disperse so well. Spiking is beautiful for homogeneous samples. Water, plant oil, blood, by the way, blood plasma. Yeah? So some biological samples also, saliva, I think. Urine can be spiked quite nicely and so on. So whenever it's homogeneous, always easy. But then dispersing is not really an issue. Also, natural water is pretty okay and so on. But for example, if you're analyzing some rocks, not easy. Or soil. Soil is terrible. I keep bringing up soil all the time because it's so nasty in so many ways that it is well usable for all demonstrating all kinds of nastiness, yeah, that can happen. Okay. Finally, what also is pretty useful sometimes is interlaboratory comparisons. Here, of course, it depends a lot what type of interlaboratory comparison it is, whether it operates with independent reference value or consensus value. We will come to those terms later on. But most of the time, you cannot get so accurate data from interlaboratory comparisons. So usually, you cannot really determine bias with laboratory comparison. You can get some idea about, okay, it's probably not big enough or something like that, but usually you cannot determine. Any questions here? Okay, certified reference materials are a big part of this. I will explain much more about them. Spiking also will come later on. Interlaboratory comparisons, another big part of this course, so that you will hear about these things more in the future. But I simply wanted to very briefly explain here, just to give it to you very clear understanding that whatever you can do to have as many uncertainty sources inside this SRW is very good if you manage to get as few of them in bias, because bias is more difficult. And yes, you can sometimes be as lucky as this. This is really nice. And you don't really have to do much any modeling or anything. If you manage to determine that you have negligible bias, then SRW is your measurement. That makes your lab's life very, very easy, actually. But you have to demonstrate that bias is negligible. Otherwise, it doesn't work. All right. And now I have 2 slides, and I think I will manage to cover them in 10 minutes. And then we stop here. Yeah, and sadly, we today did not manage to start calculations, but next Tuesday, now it can be almost sure that we will do calculations. So bring your laptops. And also let me announce that now I have updated. I made some changes really. The slides measurement uncertainty part 3. The measurement uncertainty part 3 slides are now already in Moodle, so that you can download. And actually, yeah, it can happen that next time maybe we already will start with measurement uncertainty part 3, so that you can already download from. Okay, but now, yeah, let us come to some more terms. So we've been speaking a lot about precisions of different kinds, and I've spoken something about systematic effects which relate to trueness. And now let's look at these terms, and then here is a slide full of terms. Yeah. So this slide I hope is actually very well understandable for you. These values are not precise because they do not match with each other. They are also not true because they have bias. They are systematically off. And accuracy is a term that needs or encompasses or embraces both trueness and bias. You can only call result accurate if it has good trueness and good precision. Yeah. The next way is here. Okay, precision bad, trueness good. But since precision was bad, accuracy is still bad. Next thing, precision good, trueness bad, but accuracy again bad because one of them was bad. Only here, when both precision and trueness are good, only here we can call our results accurate. You might now say, hey, wait a minute. Why are we not calling this result accurate? Because the average matches the true value very well. But the term accuracy refers to every one of these individually. So all of them individually must also be close to the truth. The point is that when you determine precision and trueness, you make lots of replicates, yeah, and okay, your average of your replicates might even be fairly close to the true value. But with your routine samples for the customer, you often make kind of 2 replicates, maybe only 1 measurement, maybe 3, but usually not more than that. So that accuracy refers to each and every one of those. They must all be okay. Therefore, here we can say that this. Please raise your hand who understood this key. People on the internet? Either? Okay, good. Then, let's look here. This is now a lot of terminology. So, first of all, our measurements are influenced by errors. Errors shift our measured value from the true value. Errors can be systematic and can be random under certain conditions. As we saw, these terms are not absolute, but let's say under some specified conditions, we can, let's say within a day, then we can clearly distinguish what is systematic, what is okay. And these errors then together, by combined together, make simply error, sometimes called total error. Okay. Now, how do we characterize our method in terms of these error types? The random error we characterize by precision. So all those precisions that we looked at, they characterize random. The systematic error we characterize by something that's called trueness. Here, these two terms together give us accuracy. So if result has good precision, good trueness, it has good accuracy. Finally, how do we quantitatively express those performance characteristics? Precision we almost always express by standard deviation. Yes, it can be different types of standard deviation, but it's still standard deviation. Trueness can be expressed either by bias. Bias is simply difference between your obtained value and a reference value, not true value, reference value. But also, essentially as good, simply expressed mathematically in different way, is recovery. Bias or recovery. And if now all this information, both systematic error or trueness information, precision information, is combined in an intelligent manner, you can get measurement uncertainty. And measurement uncertainty can be considered as quantitative evaluator of accuracy. And here again, I'm at odds with some gurus, because there are people who say accuracy is a qualitative term. It cannot be expressed quantitatively or numerically. And what I'm just now explaining is not true, yeah, they say. I say that, in my opinion, it's very useful to express it exactly this way, because it makes a lot of clarity. This whole scheme, actually, in my opinion, it's a very nice scheme. Brings in a lot of clarity into terms. And at least in this course, accuracy is quantitatively evaluated by measurement uncertainty. And this is, by the way, not I did not invent this scheme. It was invented by some colleagues, yeah, and was published quite a long time ago, actually. So this comes from this publication. I've a little bit modified here, but in principle. Any questions here? Yep.
I wanted to clarify, maybe it's more of a linguistic question, but I was kind of more accustomed to accuracy being switched. Accuracy presenting the systematic error and trueness.
So good that you asked. Yes, I should have explained that also. This logic is, let's say, is used in Vim, which is like the #1 terminology resource, if you remember the very, very first lecture. And also in a number of other documents. But then there are also guideline materials where people would write accuracy into this column. So in many documents, the term accuracy means exactly the same way, or exactly the same thing as in our course is trueness. And this is actually a very sad thing. And since in both camps there are very prominent people and both camps have very prominent organizations, and of course nobody wants to give up, yeah. So it's not really a fight. They are not really fighting literally, but they still simply keep their position. So there are two groups of people in the world. One say, yeah, this is trueness. Yeah, what I mean? No, this is accuracy. Yeah. So take care. Yeah, you will encounter, like FDA validation guideline, by the way, is one of the, which is very important one actually. Validation guideline would write into this column accuracy. But I'm not really sure whether, now Gleb said that trueness would now come here. Here I'm not so sure that this is.
Maybe I just, that third column at all, maybe.
Yeah, I think so, yes. Very often the third column is not presented in such schemes. They only speak about precision and trueness in one set of documents, or precision and accuracy in another set. According to Vim, accuracy is essentially closeness of your measured value to the. So, any questions before we close? If not, thank you. Yeah. And we will meet again on Tuesday, and bring your laptops, and we maybe start with uncertainty part 3. Maybe yes, maybe no. Okay.